Today we're going to take a look at applying those implicit differentiation techniques that we saw in yesterday's videos using what is called related rates. And what related rates really are is we are looking at a situation where the rate at which the variables are changing those rates are related to another variable. And usually, not always, but usually that is t time. And so what we're going to end up doing is we are going to take the implicit differentiation where our variables are functions of t. We're finding our dx dt and dy dt's along the way. Yesterday we just focused on dy dt and solved for that one. Today we're going to see dx dt, dy dt, or whatever variable dt we're working with. So let's just start with a very fictitious example. We will say that x and y are functions of t, where x equals 2, y equals 3, and dx dt is equal to 13. We're going to find dy dt. And the function we're going to work with, just to get us started, is going to be xy squared plus y equals x squared plus 17. So we're going to differentiate this implicitly. Remember, the derivative of x is dx dt, the derivative of y is dy dt. And so when I look at this first product, x times y squared, we take the derivative of the first. The derivative of x is dx dt times the second, y squared, plus the derivative of the second is 2y times the derivative of y, which is dy dt, times the x, plus the derivative of y, which is dy dt, equals the derivative of x squared is 2x, and then we multiply by the derivative of x, which is dx dt. And the derivative of 17 is 0. Now, what we did yesterday was probably more difficult because we had to go through and solve for the dy dt using a lot of the algebra. The algebra here is going to be a lot simpler because we actually know in this differentiation that when x is 2, y is 3, and dx dt is 13. So dx dt is this first factor here, that's 13, times y squared, y is 3 squared, plus 2y, y is 3, and I'm going to multiply the x also here as 2 times dy dt, plus dy dt, that's what we're solving for, equals 2x, which is 2, times dx dt, which is 13. Because we are given all these numbers, it's going to help it simplify much nicer. When we multiply 13 times 3 squared, that's 13 times 9, which is 117. Plus 2 times 3 times 2, that's 12, dy dt, plus the dy dt equals 2 times 2 times 13, that's 52. Combining like terms then, we've got dy dt's together to combine, so we have 117 plus 13 dy dt's equals 52. And this is going to be much easier to solve than what we saw yesterday. We'll subtract 117 from both sides. And 13 dy dt is equal to negative 65. Divide both sides by 13, and dy dt is equal to negative 5. Now, this example, I gave you an equation and I gave you the variables, so it really didn't have much meaning other than, hey, a nice little fun exercise to find dy dt. And it worked. However, usually what we're going to have is we're going to have a situation where we have to generate the equation based on information we know, based on relationships that we know from our past study of mathematics or other fields. So, for example, let's do an example that's a little bit more applied. Let's say a rock drops into a lake. When this happens, the ripples are going to come out from the center in pretty much a circular shape. We're going to assume it's a circle. And we're going to say the ripples expand outward at 2 feet per second. We are going to find the rate of change of the area of this circle when the radius is 3 feet. Specifically, what we're interested in is finding the rate of change of the area. That's what we're looking for. So we're looking for how the area changes, dA, over time, dt. That's what we're looking for. The change is going to be a derivative of the area with respect to time. What we know about the area is area of a circle is equal to pi r squared, which you know is silly because pi r round and cake r squared, but that's my best math joke you get in a video. Area is pi r squared. We also are told that the radius we're interested in is 3 feet, and that the ripples are extending at a rate of the change in the radius over time is extending outward at 2 feet per second. So the radius is changing at 2 feet per second. The radius is 3. We want to find the change in the area. So we take the implicit derivative. The derivative of A is dA dt equals pi is a constant. The derivative of r squared is 2r dr dt. And then we just plug in what we know. We're looking for dA dt equals pi times 2 times the radius, which we found out was 3, times dr dt, which we know is 2. And so the change in the area with respect to time at this moment when the radius of the ripples is 3 feet is 12 pi, or approximately 37.7 feet per second. That is the change in the area over time when the radius hits that point of 3 feet. That's all we're doing with implicit differentiation, is we're identifying our equation, what we know, and we're finding the piece we don't know. So let's try another example. This is one of the classics of calculus problems. Every calculus student gets to experience this problem. A 30-foot ladder. is sliding down a building at a rate of 5 feet per minute. So here's our building. There's the ground. The ladder leans against it, and it's sliding down at 5 feet per minute. It's slipping. So as the top slides down, the bottom also is going to slide out, because the ladder can't get shorter. What we want to know is we want to find the rate of change of the horizontal distance from the building when the base of the ladder is 30 feet from the building. So, I'm sorry, I said a 30-foot ladder, 30 feet from the building. It's on the ground. Let's change the height of the ladder. Let's make the ladder 50 feet. It's got to be bigger. So the idea is the ladder is sliding downward at 5 feet per minute. How fast is it sliding outward? And most students say, well, it seems like if it's going down at 5 feet per minute, it should be going out at 5 feet per minute, right? Well, not really. Let's look at what we know. We know the ladder is 50 feet. We don't know x or y, but what we do know is how x, y, and the 50 are related. We've got this Pythagorean theorem that x squared plus y squared equals 50 squared. We also know that the base of the ladder is 30 feet from the building at this moment. Now it's sliding, but at this moment it's 30 feet from the building. So x is equal to 30. What's y at that point? Well, the Pythagorean theorem will tell us that 30 squared plus y squared equals 50 squared, and 30 squared is 900, plus y squared is 2500. Subtract the 900 and we get 1600, so y is equal to 40. So that's just basically using the Pythagorean theorem so that we know at that point when x is 30, y must be 40 for the ladder to be 50. The other piece of information we're given is it's sliding down the building at a rate of 5 feet per minute. Down the building, that's the change in the y. That's how the y is changing, going down the building. So we will say dy dt, the change in y, is 5 feet per minute, and it's going down. To represent it going down, we'll make it a -5. So now we'll take a look at our function and take its derivative implicitly. The derivative of x squared is 2x dx dt. Always multiplying by the derivative of the variable. The derivative of y squared is 2y, that's plus 2y dy dt, equals the derivative of 50 squared is 0, because that's a constant. And then we just have to plug in what we know. 2x, x is 30, dx dt, that's what we're looking for, how it's changing horizontally, plus 2y, y is 40, dy dt is -5, equals 0. So when we multiply, we get 60 dx dt minus 400 equals 0. Add the 400. 60 dx dt is equal to 400. And so when we divide by 60, dx dt is equal to, reduces to 20/3, or 6.67 feet per minute. So when the ladder is going down the building at 5 feet per minute, the way it's going away from the building is going to be variable, but at the 30-foot moment, we're exactly 6.67 feet per minute away. Let's try another example. We got to do a business example. This is business calculus after all. So let's say a company is increasing production at a rate of 50 cases per day. This is because the demand is P equals 50 minus Q over 200. And like we've seen all quarter long, P is the price and Q is the quantity demanded. We are going to find how increasing the production 50 cases per day, how is that going to increase the rate of change in revenue? When production hits, let's say, 150 units. So we're increasing 50 cases per day. That's going to remain constant. But what it's going to change in a variable way, it's going to change the revenue. So we want to know what is that rate of change in the revenue at the point when we have 150. Well, you'll remember that revenue equation is equal to the price times the quantity that we sell. Price times quantity is revenue. So we've got an equation for P, so let's plug that in. P is 50 minus Q over 200 times Q. And so when we distribute, we get 50Q minus Q squared over 200. This is our function we're going to work with. What do we know? We know we're increasing production at a rate of 50 cases per day. That's something's changing over time, 50 cases per day. It's the change in the quantity, the number of things produced. So the change in the quantity over time is equal to 50. We're also interested in when production hits 150 units. That is our quantity, which equals 150 units. So we've got this equation, R equals 50Q minus Q squared over 200, and we are looking for the change in R over time. dr dq. How is the revenue changing? Well, if we take the derivative of R is dr dq, dr dt, equals the derivative of 50Q is 50 dq dt minus 2Q squared, 2Q is the derivative of Q squared over the 200, and then times the derivative of the Q, which is dq dt. Plugging in what we know, we're looking for dr dt. We want to know the change in revenue over time. At 50 times, the quantity is changing at a rate of 50 per day, minus 2 times the quantity currently is 150, over 200, times the change in the quantity is 50. And if we plug that into our calculator to get our total revenue, 50 times 50 minus 2 times 150 times 50 divided by 200. And we get 2,400. Oops, I'm sorry, I lied. 2,425. There was a change of $2,425 per day in revenues, as long as we can keep increasing production by 50 cases per day. So that's related rates. It's a really short video today. A nice reprieve after a couple long videos probably. But the idea is we have to come up with an equation to model the given information. Take what we know, take the implicit derivative, and start plugging in our values. Take a look at the homework. Try these out. If you don't do these in advance, you won't know what your questions are in class. Take a look at the homework, and we will see you in class tomorrow.